What is electronegativity? That may not have sounded like a question. That was a question. What is electronegativity?
The ability of an atom to take bonding electrons from another atom?
Yeah, okay, that's it. It is one of the most important concepts, in my opinion, in chemistry in general, the ability for one atom to steal electrons from another atom. Okay? It's a fascinating topic. It's pretty much an entirely human quantified invention, okay? But it is very, very important to understanding how atoms interact. Okay? It is so important, it should be a centerpiece of all textbooks. And to the best of my knowledge, our textbook doesn't cover it. Okay? Which is a big, big flaw in our textbook. Okay? But electronegativity is a very important concept. It's what describes how we build structures. It's what describes how we get reactions. Okay? The numbers associated with each atom as an electronegativity are kind of arbitrarily determined. Okay? It's not perfectly arbitrary. They are calculated in some way or another. But depending on which way you calculate it, you might get a different numerical value. So if we look at this table, fluorine has the numerical value 4 written under it. That's not its atomic mass. That's representing its electronegativity. You'll also notice that fluorine in the kind of three-dimensional stair step is the highest one here because 4 is the largest electronegativity on this scale. Okay? So it's trying to represent those electronegativities both visually, okay, through a visual design element or an aesthetic element with those heights, and then also quantifying it underneath. Okay? The general trend is that fluorine's the most electronegative, and then the complete opposite corner, cesium, is the lowest. That is not a perfect trend. Okay? There are exceptions to it, but that holds fairly true and fairly accurate. Okay? Which means we could interpret different electronegativities in different rows or columns by using this trend so long as it tracks appropriately with our trend. Re-exam 1, I believe it's short answer C, you should now be able to go through and think a little bit more carefully about why that question exists. Okay? For those of you wondering why that came out of left field, it was in the Lewis structure video, actually. Okay? Which you probably should have gotten wrong in the Lewis structure video. Okay? That's how it was designed. Okay? So one of the ways that we can calculate electronegativity is to use information from another source. Okay? That other source is our ionization energy, and we'll see here in a second, electron affinity. Ionization energy is the energy required to remove an electron. It sounds kind of like electronegativity. Electronegativity is the ability from one atom to steal an electron from another atom. Isn't that the same thing as ionization energy? I'm removing an electron, am I not? What's the difference?
We're calculating the amount of energy needed to take it.
So in ionization, we actually have a quantification of energy as opposed to just some weird mathematical mumbo-jumbo. That's a difference. What else?
It increases as you go about.
That's looking at our trends.
Is it because electronegativity, you have to take bonding electrons? Ionization is just an electron?
Yeah, exactly right. Electronegativity is looking at a bonding electron. You're taking one electron from one atom and giving it to another atom. Where's the electron going in ionization energy? Silence is a surprisingly accurate answer.
The gaseous thing.
The electron is going away. Okay, it's going outside of the atom. It is going into nothing. What's our name for nothing? Begins with a V. The vacuum. Okay? So there is no other atom present. This is just how do I remove that electron? Okay? There's a couple things on this slide that bother me, largely because I think at first I just copied it from the textbook and I really shouldn't have done that. Okay? I really don't like the stuff in blue. It bothers me a lot, so we're just going to erase that. Okay, so let's take a look at these trends. Ionization increases as you go from the bottom to the top in a group. Okay? So let's take a look at lithium versus hydrogen. Okay. What is the electron configuration for hydrogen?
1s1.
1s1. What is the electron configuration for lithium?
1s2 and 2s1.
Okay. So those are our electron configuration. We can actually use this information to predict what's going on with the ionization energy. Okay? Which electron am I going to remove from hydrogen if I'm looking at ionization energy? There's only one. That's a stupid question, Mike. Yeah, it's the only one there. That's the one we remove. I completely agree. Okay, so thanks for calling me out for being an idiot. I appreciate that. Okay?
Anytime.
Lithium. Which one?
2s1,
Why 2s1?
because the furthest one out.
We're looking at the highest energy electron. That's the one I want to remove when looking at ionization energy. I don't care about the internal ones. Okay? So we're going to remove that. Thank you. I feel a little hot too. All right? Right there with you. Okay? It must be the coffee pot. Which of these is going to have a higher ionization energy?
Lithium.
Okay? So we've got a vote for lithium. Well, it's at a higher number, so it must be a higher energy. Okay? Remember how we drew out the pictures of our elements? We said we had the nucleus. Where's our first electron?
The first, is it the sphere?
The first energy level. Okay? As we continue, what happens? What comes after the first energy level? The second energy level. For those of you going like, is that really all? Yes. The next energy level. The third. The fourth. Fifth. Yes, those are progressively getting smaller. I apologize. 7. Vacuum. Okay. If I take a look at hydrogen's electron, we'll call it red. Where would it be in my diagram? At the first one. We'll make lithium blue. Should have color-coded it earlier. Where's its electron that we're talking about removing? 2. When we're talking about the ionization energy, I'm talking about the energy required to take the electron from there and move it to the vacuum. For lithium, I'm talking about the energy required to move from here to here. Which one has the higher energy? Hydrogen. It's got a larger jump. Okay? A picture can be worth 1,000 words. This is why I drew out the picture early on, is to give you that understanding behind it. Okay? We run into confusions. Almost everybody jumps and says lithium's the first answer because it's at a higher energy, which means to jump is going to be a shorter energy. So we have to be a little bit careful about the numbers that we see. We can't just say a bigger number means more energy. That's not always the case.
So in essence, it's kind of like weightlifting. The heavier you are, the more energy you're going to need to.
Or it's easier to pick up from your waist to your shoulders than it is from the floor to your shoulders.
I'm not sure I want to get into that example. I know where you guys are going with it, but I think there's too many moving parts in that one. Okay? So when we look, the ionization energy increases as we go from the bottom to the top. Well, where's lithium? It's lower on the table than hydrogen. So when I go from lithium to hydrogen, what happens to the ionization? It gets higher. There's our direct evidence. If we throw in cesium, that goes all the way up to the 6th energy level. That energy gap is now very, very small. Okay, kind of makes sense? Okay. So one of the things I like about this is that we can use this exact same logic to explain both trends. And since you're taking a picture, I'll pause for a second. Are you good? So, and actually before I fully erase that next one, the next trend is of course going to talk about left to right ionization. All we've talked about is up down. So now we have left to right. Well, based off of this, what would we expect our ionization energy to do? So we'll start again with lithium. We'll do it in blue. We have 1s2, 2s1. What's the other element you want to use? Problem with sulfur?
Of course it is.
Look at the periodic table. What's the problem with sulfur? Everybody's looking at sulfur. Remember, we're doing a comparison to lithium.
It's lower in the.
Sulfur is not in the same row as lithium, which means we're going to have a column and row differential. That's going to make it a lot harder to interpret, so that's why I'm going to say no to sulfur.
I totally meant carbon.
Totally meant carbon. Cool. So let's switch it up to carbon. Does green show up okay? Yeah. Okay. 1s2, 2s2, 2p2. Right? Where's carbon's last electron?
Third.
It's jealous.
In the third level?
Oh, no, I'm sorry.
It's in the second level.
Second
So
level, second.
what you might be talking about is the second sublevel.
Sublevel.
In our argument here, are we talking about sublevels? No, we're only talking about the energy level. So for carbon, the last electron goes into which energy level?
2.
The second energy level. So there's my carbon's electron. To go to the vacuum, I know there's a bunch of letters in the way and all that. Should it be different than for lithium? No, it's the exact same. So we don't expect to see a difference there. Right?
Why
But of course it doesn't do that. Something else goes on. What else happens as we move left to right within a period? What happens to the size of the atom? It gets smaller because there's more protons, which means our first approximation of that energy level is not that the electron is located there, but that it's a little bit closer. The second energy level for carbon is actually lower, which means
It has a bigger ionization.
its ionization is actually larger than that for lithium. So we're using information from our electron configurations and ultimately atomic radii to come to these conclusions. And if we go through and actually finish that erasing, as we go from left to right across the period, what happens? It increases. That's exactly what we just established. Okay? So there's a lot of stuff up there, so I'm going to clear everything. And I'm going to go back and erase this because I don't like the stuff in blue. Does anybody see a problem with memorizing these trends?
You could probably get a mix match with electronegativity.
You could potentially get a mix matched with a different system. I would argue there's another big issue. There's some linguistic cues in here that we could take advantage of. I'm going to argue increase and decrease is not a linguistic clue because everything does that. What is special about these trends as they are written?
that you can confuse group and period?
What does in general mean?
Most of the time.
Most of the time. There are exceptions. Okay? And that's usually the conclusion that people jump all over is that there are exceptions to this. There are no exceptions to ionization energy. There are exceptions to a man-made rule for overlaying on top of a system where you don't want to understand what's going on. Okay? So let's take a look at what's happening so we can fully address what's going on with this. Okay, so we see a chart like this, and it can be a bit confusing to look at. Our atomic numbers running along the bottom. So an atomic number of 1 would correspond to what element? Hydrogen. So that first dot is hydrogen. An atomic number of 2 would be helium. If I now do a little connect the dots, what happens is I move left to right for that first row. What happens to the ionization energy? It increases. Is that what the trend said?
From left to right?
Left to right.
Yeah.
Yes. Sweet. Perfect. Beautiful. Okay. I go to 3, I would get lithium. So I go from hydrogen to lithium. What happens to the ionization energy?
Bottom.
It decreases. What does our chart show?
It decreases.
It decreases, right? Lithium to sodium, decrease, 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 decrease. Notice it's not perfectly linear. We don't really care about that. The trend just says it decreases. Does it decrease down a column?
Yeah.
Yes. Right? And the reason it's decreasing is you're looking at a new energy level each and every single time. Right? If we look within a period, what happens? Lithium to neon. Same period. What's our general trend? It increases. That's exactly what we were told to memorize, right?
Yeah.
Does it always increase?
No.
Apparently not, because
Apparently not, because
there's some dips.
there's some dips. We see some dips in here. Okay? It's going down in that case. In this case, it's going down. There are these exceptions, and we go, oh, we'd have to memorize these exceptions. And I would argue you don't have to memorize the exceptions, but you have to understand a little bit about Disney. What did I just say? Disney?
Yeah.
We need to know a little bit about Disney. Yeah. Yeah, we need to understand a little bit about Disney. All right, so let's take a look at one of those exceptions. Which one do you want to see, red or blue? Blue, okay. Blue, I will admit, is the more challenging one. Okay? It works both same in either cases, so it's not a big deal. Okay? In the blue, which elements are we looking at? Where's that dip happening? Lithium, beryllium, boron,
Nitrogen to oxygen.
carbon, nitrogen, oxygen. So we're talking about nitrogen, and we're talking about oxygen. Okay. Remember, my whole thing was we could use ionization or electron configurations to evaluate this. So our very first step is going to be, let's look at the electron configurations. What is the electron configuration for nitrogen?
1s2.
Whoops.
And then 2s2. And then 2p3.
All right. And here's where it's going to get a bit weird for this example. What we're actually going to do is full on look at that last 2p orbital, or that last 2p section. We're going to break this down into all three orbitals, because the p has three orientations. So if I'm going to place those three electrons in there, I'm going to get 1, 2, 3. Why are they half filled? Why not have done something like that? Whoops, that was the wrong eraser. Does everybody get what I'm trying to represent here? Okay. So the 2p orbital, how many orientations are there? Come on. 2p. What does a p orbital look like?
It's the dumbbell.
It's the dumbbell. So we have the p on the y-axis, we have the p on the x-axis, and we have the p on the z-axis coming in and out of the plane. Yeah? So when we're talking about looking at the electron configuration, we actually have to go through and look at the actual orbitals that are being occupied in nitrogen. So there's three orientations. There's orientation 1, 2, 3. We could call this X, Y, and Z. Yeah? Okay. I need to place 3 electrons into those orbitals. One option, 1, 2, 3. Right? Everybody okay with that? Okay, so I'm going to undo that, because the second option is 1, 2, 3. Which option is correct, first or second?
First.
Why the second?
Because it fills up all boxes.
What's that?
Because it fills up all boxes.
Did it matter, though?
Getting to symmetry, does it matter, is an important question. Yes, it does. Okay. When we looked at our electron configurations, we had our first energy, our second energy, our third energy, our fourth, right? Where's the first electron go? The first energy. Where's our second electron go? It didn't go to the second. Where did it go? Stayed in the first. Why did you want to place it in the second? Because I like that thought. No, sorry, I don't accept that thought.
The second energy level of
What's the charge on an electron?
-1.
Negative. What's the charge on another electron?
Negative.
Do those electrons want to be near each other?
No.
No. Same charges repel. So why would you want to go into the second? Because there's already an electron in the first. So we'd move it to the second so that it doesn't have to interact with that other one. But that means we can't fill all our orbitals appropriately, right? So what did we end up having? We brought in this concept of each orbital holding 2 electrons. They could hold it because spin states go in the opposite direction. Right? So we would fill lower energies before promoting to a higher energy. When we look at the 2p, I put my first electron in. There it is. Where's the next electron go? Right? If it stays in the same box, I'm saying the next place to place the electron is higher in energy. Is that true? No. All of those p orbitals are the exact same energy. So I'm now giving you an option. You can either sit immediately next to Joey or somewhere else in the room. Right? Where did you all sit? Sorry, Joey. Somewhere else in the room. Why? All equal energy. Right? What if instead, when you walked in, Joey was sitting here, he had his chair, every other chair had a massive thumbtack placed on it that you could not remove? Where are you going to sit?
Where there's not a thumbtack.
Not where there's a thumbtack, right? Which is?
Hi, Joey.
Right next to Joey. There you go.
Valentine's Day.
Okay. Why did you not sit on the thumbtack? That's going to hurt. There's more energy associated with you sitting there because you're going to have to constantly maybe position yourself so the thumbtack doesn't stab you. You'd have to sit very, very carefully and never shift. Okay? Or you sit next to Joey where you don't have to worry about it. Okay? So in the case here, all of those seats are the exact same energy, which means the electron's going to be like, do I really want to pair up, or am I going to have more space somewhere else? So it decides to fill singly first. Now where the next electron would it go? Ugh. You process what I said there? Where does the next electron go? It's going to go back into any one of those. We typically read left to right, so we would place it in that X. Okay? So when we look at our electron configuration for nitrogen, yes, that's correct, but what we're now identifying is that those p orbitals are all half filled. What happens if we move to oxygen?
So it's 1s2, 2s2, and then 2p4.
Oh, interesting. What do we end up encountering right away? The exact example we just talked about.
But there's 4 now.
And of course I didn't switch the colors. God damn it. 2p4. There's 1, 2, 3, 4. Yeah? This is getting hard, Mike. Why are you going into this detail? Here it comes. Ionization energy, what do we do? What is the definition of ionization energy? The energy required to
Remove an electron.
remove an electron. What happens to our nitrogen? If I lose an electron, it becomes? So one option, we could go through and say, well, we'll remove an electron, 1s2, 2s2, 2p2. We'll still have to go through and look at our nice little pictures here. Box 1, 2, 3, 1, 2. I would argue you can tell me some information back here about that nitrogen. What can you tell me about it?
If it's
Positive charge?
It is positively charged. How'd you come up with that?
You're taking away a negative charge, aka the electron.
Electrons are negative. We're taking away a negative. We've now become positive. Ionization energy will always make your atom positive. Okay? Now we move to oxygen. What would happen to oxygen when I take away an electron?
It'll remain the same because you're taking
If I take away an electron from an atom, what happens to it?
Kind of positive.
Becomes positive. When? Always. Will always be positive because I'm taking away an electron. So this becomes 1s2, 2s2, 2p, 3. And our pretty pictures of boxes? Disney. No? No. Okay. Let's push this a little bit further. You looked at Disney princes or princesses, right? We've all seen some Disney. Yeah? If you're like, I don't want to think about Disney, that's okay. Think about the most attractive person you know. So in this example, when I add that, stop looking at me. That was nice, Joey, to turn around and look behind you. That was Valentine's. Okay. If you cut their face in half, what is it, figuratively? Figuratively, don't do it literally. Okay? And you reflect their face across. What happens?
Depends on symmetry.
Okay? Not in Disney. Okay? And we're talking about looking at Simba because you think Simba's cute. We're not cutting through the belly. We're cutting through the face. Across that nose line. What happens?
You kill a lion.
You reflect it. It's an animation. You get the exact same face, okay, as if you hadn't done it. They are perfectly symmetrical. It works great for Disney because what does Disney do? They idealize everybody, so it's perfectly symmetric. If you look at the most attractive people in the world, why are they attractive? Symmetry. Okay? No one's running around saying, yay, Quasimodo. Okay? That's a Disney character. Damn it, it just fell apart. Okay? We have to recognize that symmetry is important. And you're like, well, that's humans. Humans care about symmetry. Guess what? Chemistry does the exact same thing. Chemistry also cares about symmetry. When I go through and take a look at that nitrogen, I've got those 3 orbitals. They all have electrons, right? Is that symmetric then? They're all half filled, yeah? That's pretty symmetric. Everything is balanced out. Everything has 1. That is symmetric, so that becomes beauty. That's beautiful. What happens when we move to the nitrogen plus?
It's ugly, but it's not symmetrical.
It's ugly, it's not symmetrical. This is Disney, we can't use the word ugly. We now have a beast. What happened in the case of oxygen? Where did oxygen start? Is it perfectly symmetrical? No. So what did it start as? What happens when I remove that electron? Becomes symmetrical. It is now beauty. So what we're talking about when we're looking at these ionization energies is we are looking at transitioning from becoming a beauty to a beast or a beast to a beauty. Okay? Both of these are going to require energy. We can't just magically happen. There is no fairy godmother. Okay? So let's take this analogy a step further. I have a magic beat stick, and I'm going to come up to you with this magic beat stick. Okay? Let's imagine that you're beautiful. Okay? You are beautiful. But let's say, man, I need to stop digging on that one. Let's just run with it. There you are. You're beautiful. And I'm going to come at you with my magic beat stick, and I say, if I hit you with this magic beat stick, you will become a beast. How many of you are going to be like, yep, sign me up? You're like, no, you can't hit me with that. You're going to fight back. Okay? Which means there's going to be more energy going in. So when we look at nitrogen, it needs even more energy to ionize because we're forcing it to become a beast. It's not happy about that. So its ionization energy spikes. Okay? What happens to oxygen? Now imagine you're all a beast. I come up to you with my magic beat stick. And I swing it, and I tell you, if I swing this at you and beat you with it, you will now become a beauty. Are you still probably going to fight me? Probably because
You're gonna hit us with the
I'm going to hit you with a stick. You're not going to like that. And some people, I'm not going to accept that. Lots of people do. This is why we have
plastic surgery.
plastic surgeons. Okay? When you get plastic surgery, there's anesthesia for a reason. They're hitting you with a beat stick. Okay? That beat stick all of a sudden, though, makes you beautiful. What happens? Okay? Your energy goes, yeah, I'm not going to like that, but maybe the suffering's worth it, so I'm not going to fight back as much because you now become beautiful. Same thing happens to the oxygen. Oxygen comes with ionization energy. Yeah, that's going to hurt, but at the end, I become symmetric. So I'm not going to fight as much. What happens to the ionization energy? It drops a little bit. So each of these exceptions is a transition between a beauty and a beast. Okay? If we get a transition where it seems to be spiking, it's because we're taking something that was already beautiful and we're turning it into a beast. Okay, it's going to fight the system. For those where it looks like it's dropped suddenly, we're at a transition where we're starting at a beast and it's becoming beautiful. Disney. Okay? So we can use the trends and memorize them if we so desired. We don't have to memorize these things if we understand where they're coming from. They're coming from those electron configurations that everybody hates drawing. Okay? Are you required to know this kind of Beauty and the Beast kind of aspect? So some head shakes yes, some head shakes no. I'm going to get a nice even mix here. Are you required to know everything that I say?
Probably.
No. Right? Do you want an A in the class?
Yes.
Are you required to know everything that I say?
But that
Yes.
makes it easier to understand the way
Yes.
you broke it down.
Right? And so what I'm trying to do is spin it and repackage it to help it stick for you. That's my job. So we'll get at the understandings and the underlying meanings behind these things. Okay? Your responsibility is to try and decide how much of that do I want to know so that I can get the grade that I want. If you just want to pass, you need to know the trends. If you want to do better, you have to understand the meaning. Okay? And that goes for everything that we talk about in class.
And
Right.
it should be noted that Mike successfully used a story to represent scientific information and gave specific characters to these things that we don't always see.
Kind of like looking at the aesthetic aspect of science. Neato.
Go team! So he just modeled what you were supposed to be doing in my class.
Okay?
I forgot to do the beat stick, by the way, so it's
Yeah.
beat
You really seem to enjoy the beat stick. It's even better when I pull out the big metal rod and start pointing at things. Okay? So you have the underlying meaning. You can use it. Okay? There's lots of stuff that you have to process. You may decide that you don't need to memorize that because you don't need those extra points. That is your choice. As long as you're making that decision, that's on you. Okay? Make sense? Okay? So with that, we can shift to electron affinity. Electron affinity is a similar concept, except affinity is now taking that very same electron that we ejected out into the world, and now it's taking a neutral atom and grabbing it and bringing that back in. The big thing that I want out of electron affinity, because it's not in the textbook, is what does that do to the atom? I have a neutral atom and it grabs an electron.
It has to.
Becomes negative.
Becomes negative. That's it. That's what I want you to get out of electron affinity. There are trends that you could memorize with that. I don't care. Okay, don't stress about those. You could do the exact same electron configuration arguments if you so chose. Okay, you just kind of have to invert them to deal with that. Okay, so don't stress about that. So where this kind of comes into play is when we move to our compounds. Ionic radii. If I take a metal and a nonmetal and I now mix them near each other, stuff happens. Okay? That stuff happens is a chemical reaction that's tied back to electronegativity. And if we went back and looked at our electronegativities for sodium and chlorine, we would find that chlorine's electronegativity is vastly larger than sodium's. What does that mean when I put those two atoms near each other? Chlorine will suck an electron away from the sodium. So chlorine gains an electron. By gaining electrons, what does it become? Negatively charged. A negatively charged species is known as an anion. And sorry, I forgot the L. What happened to the sodium? Became positive. It's now lost that electron, and we now have a sodium cation. Okay. What this slide is referencing is what changed about each of those individual atoms. Notice we're talking about ionic radii. What determines the radius of an atom?
The protons?
No. Where are all the protons found? In the nucleus. How big's the nucleus? A marble inside the superdome. Is the marble really dictating the size of the superdome? No. So the protons aren't really dictating the size of the atom. What's dictating the size of the atom? The electrons. What just happened to sodium's electrons?
They moved to...
They disappeared, which means the radius for sodium gets smaller. I think that's smaller. Yeah, that looks smaller. What happened to chlorine?
It's bigger.
It should get bigger. Do we need to worry about all those extra complex trends that we had with atomic radii? No, why not? With atomic radii, when we're moving through our trends, what happened? We were also changing the number of protons and energy levels. What's happening when I look at sodium to sodium ion? Am I changing the number of protons? No. All I'm doing is changing the number of electrons. I don't have to worry about an extra balance with the protons. All I got to worry about is the electrons. Okay? So what they're referencing here is what happens to your radii. They just change. Okay? And how they change. That's it. Okay? Covalent bonds. In a covalent bond, we now have sharing of electrons. Okay? So this is different because now it's not a transfer of electrons, which means each atom maintains its same size. Okay? But what happens to the new compound? If we're going to share electrons, that means the electron cloud, okay, and that electron cloud is that shape. Okay? That circle represents the electrons for chlorine. And in fact, the outer edge of that represents the outermost electrons for chlorine. What's the outermost edge for hydrogen represent? The outermost one electron for hydrogen. If these two things are now going to share electrons, what must happen to those circles? It's a step larger than connect. All except combine. What's happening with those two circles?
Chlorine is absorbing.
What's happening with those two circles? Interfering is technically an appropriate, really advanced aspect of that. It's easier. Begins with an O. Overlap. That's it. They just overlap. All right, that's all we're saying, is that those electron clouds must overlap. What does that mean about the internuclear distance? It gets shorter than the individual radii of the atoms. That's it. That's all we're saying. That's it. Does that make sense?
Kind of, sort of.
So if we look, the bond length for HCl is 0.127. If we look at just the radii for each of the elements and add those up, it should be 0.136. We get a shorter distance because we have to have an overlap of those outermost electrons. Okay? It's a different bond characteristic. That's why you get a different end result or a different discussion about the bond. Questions on that? Take that as a no. Then we get this cool slide on bond energy, and this is how cool it is. Compounds and chemical formulas. What compound are we looking at up here? Caffeine. Literally why we're all awake right now. Okay? Does anybody think it's a cool idea to have to draw things like that? for the rest of the semester? No, you don't want to do that, right? Okay, so let's come up with a shorthand. What's our shorthand? Not to be like subtly hinting. Let's come up with a chemical formula. So tell me the chemical formula. Give you a hint.
Is it just the compound with all?
Where are you going, Joey? How'd you get C6?
6 C's.
Okay. Guess what the next hint is?
H. 9?
Is it 9? 3, 6. Yeah, I think you're a 10. It's all right. It's okay. Is it 2? I think it's 4. 4. Oh.
C3.
Oh, 3.
Really?
There's only 2.
2, I see 2.
There's only 2 up there, I think. And we now have our formula. Okay?
Do we have to put it by electronegativity?
Yeah, it's definitely not 6. We got 8. How many C's do we got? Because it's going to bother people. 8? Okay. So, couple questions that would kind of come out of this. Okay, number 1, are we going to see structures anymore like this?
Yeah.
At that complexity, no. Will you see structures again?
Yeah.
Yes, you will see Lewis structures. Just like you saw on exam 1, will also show up on exam 2. It is an important topic. You need to do it. What we're looking at right here for a Lewis structure is organic chemistry. You don't need to worry about that. Okay, why?
Because we're basic chemistry.
There you go. That works. So what we do is we simplify that big old thing down into this formula. You guys just process this formula. This formula had a lot of meaning in it. Okay? You were able to tell me 8 carbons. You were able to tell me 10 hydrogens. You were able to tell me 4 nitrogens. Okay? And I won't name names. But you did not tell me 8 hydrogens, 10 nitrogens, and 4 oxygens. Feel free to look at exam 1, Lewis structure. Okay? The number in the lower right-hand corner corresponds to the element in front. The number does not correspond to the element after it. That is wrong. Okay? Be careful when you go through and do your exams to take advantage of that information. If you start transposing that, you will get wrong answers. It's an easy mistake, high stress on an exam. Okay? So take a minute, breathe, and make sure you acknowledge that information. Right?
It's following the syntax.
So using, the syntax of our system. If you start switching the syntax, everything goes to hell. You're using a different syntax than the rest of the world does. You lose communication. So?
The way we structured it was correct or was incorrect?
Yep. The way we've structured it here was correct. Okay? If you go back and look at exam 1, that very first question on Lewis structure, I got a lot of people saying that 8 meant there were 8 hydrogens. Okay? It is an exceptionally simple mistake to make, particularly on an exam. Be careful, breathe, don't make the mistake again. Okay? Did we lose information by going to the formula?
No. Well, I mean, we lost where the atoms would be, or the bonds would be structured.
Have I lost information about where those objects are? Yeah. So when we go to a formula, we lose a lot of structural information. We don't necessarily know how those things are connected. Okay? What we've decided is that we don't care about that information in this class. Okay? So be cognizant of that when you look at a chemical formula. It's lost a lot of information. It's just easier to represent. Okay? So let's take a look at some formulas. The top 2, relatively straightforward, match the ones we just looked at. What is different about that bottom left?
2 H's.
The H's aren't all grouped together. Why would we have done that?
to show that they have different bonds with different elements?
We could start to call out something about their connectivity, right? Where those things are connected or how they're connected. I would argue this formula in particular, the blue one, is not doing that. The purple one is. The purple one is talking about connectivity. What is the blue one talking about? Groups 4 and 5 in the English class should be able to answer this question a little bit faster than the rest of us. Why should groups 4 and 5 in the English class be able to answer this? If you're in group 4 or 5, you should be like, oh shit.
Is it like the negative, they have some negative or a positive?
No, unfortunately not.
Because it combines a hydrogen, oxygen, and
Right? Does group 4 and 5 want a little help? I'm going to take that as a yes. AQ means aqueous. If I have AQ in the back and hydrogen in the front, I have right? By changing the order of where the elements show up, I can change the meaning of what I'm looking at. In this case, I'm saying that that is an acid. Right? So switching up the order can happen. Don't let it freak you out too much. What we're trying to do is embed some more information in this without having to go all structural on it. Right? It can be a little bit challenging to deal with and a bit disconcerting because you're like, why the hell did you change it? We're changing it to draw attention to different aspects of meaning, which we may not have told you about. Okay? Same thing happens if we jump all the way down here, the bottom one, which we've talked about already. What meaning has changed in our formulas?
That one's carbon, one's water, and the other one's, I don't remember if that's carbon monoxide.
Make sure we're all looking at the same thing. What meaning has changed? It still has letters and numbers.
Two separate elements versus one compound, something like that.
Okay. These are close to each other. These are further apart from each other. And how do you know they're separate? There's a plus sign. These are two different things. This is one thing. What other meaning pops in here?
there's two oxygens in the front.
Yeah, we could reference the two oxygens.
Arrow?
What is the arrow?
It's
Going
supposed to be.
from one thing to,
It's a transition. It is a chemical reaction. Right? Looking at the bits and pieces and trying to find the meaning behind them is what we're working on. We're looking at, what is it, the smallest unit of meaning. Okay? Our morphemes. Where are those spaces? What do those symbols mean? How do we tie and use those symbols in conjunction to get to new meanings? Okay? Okay. With that, we'll hit up a little nomenclature practice. Okay, we don't have a whole lot of time here, but arguably we have exactly enough time to solve all four of these. Okay? So because you've all watched the nomenclature video, you should be able to do this starting now. Solve them all. Okay? If you don't know how to solve all of them, solve as much as you can. Okay. Please keep working on it. If you're really kind of stumped, that's okay. One of the things that I can't stress enough, when you look at questions, you must just start writing something down. Attempt to solve. Okay? If you don't know or acknowledge that it takes time, move on. Move to the next thing. Get some information down so you have something to work with. Okay? If you're entirely stumped, feel free to watch me solve these, I think before class time ends. Oh, I'm supposed to erase all my work. Yeah, 30 seconds too long. All of them are solved. For those of you that were watching, what did you see? Okay. First three were good. That's an interesting statement. I solved the first one last. If you look at how I solved, I did not solve these linearly. Went through and wrote down what I knew and moved on. What I knew and moved on. Sometimes I knew more, so I kept working. That is how you should solve all problems. Okay? You should not sit there and stare stumped or blanked at something if you don't know it. You'll also notice that when I went through and did this, how much work did I show? A lot. Lots and lots of work, and if you were watching carefully, I also screwed up on several occasions, and I even showed some of that failure in here as well. Right? I've got the work. Even with the work, solved 4 nomenclature in less than 3 minutes. Right? You should be at least that fast when doing nomenclature. Right? Which is a bit daunting, but that's where you need to be when it comes to naming. I did notice some problems with chromium. It's one of the reasons why I throw it on there. Chromium's a less common one to memorize, so people don't memorize it. Right? You now can't do nomenclature because you didn't do the basic stuff I told you to do back in Unit 1. It continues. We continue to stack information on top. You need to be going back and reviewing that old stuff to make sure it transfers up and forward. We are done. I apologize for continuing to talk, but we are done. If you got questions, you can talk to me after class.